Essentially, any material where you can have transitions from one energy level up into another energy level, pretty much, if you hit it hard enough, can be made to laze or give you some coherent light out. There are lasers based on all sorts of materials, so you can have, as I say, electronic transitions. So in argon ion lasers, this is a gas laser, and neodymium doped yttrium aluminium garnet, which is a solid laser. You can have vibrational or rotational transitions in CO2 lasers, gas laser, of course, band gap transitions in semiconductors for diode lasers, or a combination of these, so you can get tunable lasers where you can change the wavelength over a wide range using dye or solid state lasers. Dye lasers are just some sort of dye compound. For example, something like rhodamine 6G, and then it's dissolved in a solvent to make it a flowing liquid, and the liquid, as it flows, that's your laser material. Dye lasers much less popular than they were maybe 10 or 15 years ago, mostly because the chemicals that are involved can often be carcinogenic, and some of them can be mutagenic, where it's not you that gets affected, it's your children that get affected by the impact of the chemical. So nasty stuff. So dye lasers tend not to be used unless it's for a very, very specific application. Most tunable lasers now are solid state lasers, such as titanium sapphire and so on. So any material basically where we can get two or more energy levels where a photon can be emitted, it can be made to laser. Wherever we can get a population inversion, in other words, the population of the upper level can be bigger than the lower level, then we can get some sort of coherent emission, stimulated emission from it. There are laser materials, so if you don't have the feedback, then they're referred to as amplified spontaneous emission, and you can buy devices which produce that. So it's like a laser without the feedback, useful in fibre optic systems. Some of the electronics sensors guys might have seen some of these amplified spontaneous emission broadband sources. So solids, liquids, gases all can be used. Because you can use dyes, you can put dye inside a solid gelatin material. So in other words, you can make a jelly laser. So you can eat it when you're finished doing your day's work. You can just eat your laser. If it's a carcinogenic dye, then obviously that's not to be recommended. Don't try this at home. And you can also have lasers based on free electrons. So these are electrons which are free to move around, and what you do is you wiggle them backwards and forwards, up and down, and they give you light coming out. Okay. So there's loads and loads of different types of laser materials. So a table here, just to kind of go through them. You're not going to be expected to remember all these. It's just to show you the range from the ultraviolet right through to the far infrared. Further down to the carbon dioxide laser at 10 microns, and even beyond that to excimer lasers in the ultraviolet. Excimer lasers are lasers which the pumping mechanism is a chemical reaction. So by mixing materials together, you get a chemical reaction which then produces the light which you use as your laser source. The ones that are shown in bold here, these were kind of very common wavelengths, but now that everything's moved away from gas lasers, we tend to use either semiconductor lasers, solid state lasers at the right wavelength, or tunable lasers where you can change the wavelength as the laser is actually working. Okay, so tons and tons and tons of different materials that you might find in there. The pump source, we have to think about, well, okay, how do we get the energy in here? So I've mentioned the Ximers lasers. You've got the chemical reaction, which is used. Again, these tend to be nasty chemicals and so horrible to work with, but useful if you need a laser in the ultraviolet. Optical pumping I've already mentioned, flash lamps, or using another laser, usually maybe a dye laser, or a diode laser, or a solid state laser now, not so much dye. Electrical discharge, passing a current through the gas in the same way that you do with a neon light, a neon sign. And the same sort of thing in a semiconductor's injection current. You're basically passing a current through, so induced band gap transitions. And you can use very low energy photons. Remember, radio waves are just part of the electromagnetic spectrum, so these are still photons, but at the radio frequency. And these can be, because they're lower energy, these are not used to stimulate electronic transitions because they're quite high energy, but vibrational transitions in molecules. If you remember when we were talking about ionic molecules such as water, H2O, then we said that the oxygen and the hydrogen bonds, we can either have a rotational excitation, in other words, the whole molecule spins around, or the wrong sign there. Or we could have vibrations so that this arm might go into vibration backwards and forwards, and this one might go into vibration backwards and forwards, or that might go backwards and forwards, and that one might go forwards and backwards. Or the whole thing could oscillate with the arms moving closer together and oscillating backwards and forwards that way. So there's lots of different options. But these are lower energy, and so we only need lower energy excitation, so radio frequency will do. Not so common using electron beams, nuclear detonations. There were in the 80s suggestions that we should have X-ray lasers in space so that we could shoot down missiles. The energy source for that was going to be a nuclear detonation. If you want to shoot a missile down with a laser, probably still your best bet is to throw the laser at it. The technology is coming on, so that if you look at what the American military are doing, then they're getting close to the point where they can have, they've got a massive 747 jumbo jet with full of chemicals and stuff which can fire lasers and track missiles. So they're still working on it, but it's still a little bit way off. Taking the different ways in which we can excite the laser into consideration, then there are different ways, different levels of efficiency here. So for an argon ion laser, with an electric discharge, so passing a current through the gas to ionize it, efficiency of maybe 1,000th of 1%. So if you get 1 watt of laser output, you need 1 kilowatt of electrical power, and the other 999 watts goes as waste heat. Okay. There can be a problem with removing heat with power supplies and from the laser tube, so you need some way of getting rid of that heat, usually using water cooling. Water plus high voltage electricity is not a good mix, so you've got to be quite careful about how, when you're working with these systems, that you don't end up standing in a puddle of water and touch something which is live.